Alright guys, in this video we're going to talk about the process of electrophoresis. And electrophoresis is a process, and guess what? This is advanced lab methods, and we talk about processes that we do in a lab, and this is one of them. So we need to talk about the fundamentals of electrophoresis. How does this work? Why does it work, and where is it appropriate? Now, I want you to keep in mind that electrophoresis will be used again, and most of the time we use it very often in our forensic chemistry course. So this is one of the reasons that you take the summer course first, because we introduce you to the method and we don't really focus on the sample prep as much. We don't really focus on what goes on before it gets to this point in the summer class. It's only strictly electrophoresis. What do I need to do? How do I need to handle it? And how do I ensure that I get really good results from it? All of the sample prep for the extractions that are taken, the samples that are processed, and everything else that goes on with it leading up to the electrophoresis, we focus with that in CTC 210. Now, I will say, though, a little bit of this lecture that you're going to get with me in this course is going to focus on some small tidbits of information as far as samples go and what does go on, but by no means is it anything detailed. And you're going to get those details later on in a different course. All right. So the name of the game here for us right now is to talk about electrophoresis. What is it? What does it do? What kind of samples go in it? That's what I need to do, and how to handle those and process those the proper way. All right. So with that said, I'm just going to get right into it, and we're going to break this up into different chunks, and those multiple different chunks hopefully will pull all of this back together in the very end. All right. So first off, we are going to talk about electro, and that should give you an insight about what this is going to do, and phoresis. So electrophoresis, that is what this is all about. And as you can imagine, electro means electricity. That's exactly what we use. So in electrophoresis, this is typically going to carry some type of current, and that is going to generate and do some stuff, generate electricity, and do some stuff in the electrophoresis chambers that we will be using in this experiment. All right, so electro, basically, I want you to think of as charged. And they're either going to be positive charge or negative charge. And we already kind of know a little bit about this in a way. So if we are talking about charges, and if those charges are positive, then those positive things, we have a proper name for them. Now, I need you to keep something in mind. And this is where the confusion is going to happen. So if I've got an atom, and that atom is just floating around, minding its own business, it's neutral, right? But then if the atom decides, oh, well, I want an octet, I want a full shell of valence electrons, and I'm going to take my available free electrons and I'm going to kick them out, or I'm going to gain some extra in order to get this magic number of 8, even though that's a lie. Yeah, that's right. Not everything wants 8. We say that to be very general and very easy, but not everything needs 8 nor wants 8. It's just a little rule that we use when we first talk about it. All right, so if that goes on, we create a positive atom and we create a negative atom. And these are called ions, and those ions have particular names to them. And we said that if an atom is a positive charge, this is a cation. And if an atom carries a negative charge, this is an anion. So the easy way to remember that is the T in cation is positive, and the N in anion is negative. And that lets me kind of figure out what term goes to what thing is happening inside of the atoms and as they carry these charges. All right, so electrophoresis It's not the same. So, meaning that yes, we do create charges, and yes, we create an environment that is more positive, and we create an environment that is more negative. So, I have a chamber, is what we're going to call this, and the chamber is going to have a positive area, and the chamber is going to have a negative area. We are not talking about ions. We are talking about a general charge in a solution in an environment, not particular ions like cations and anions. All right, so I just need to make that clear. And that's because some of the terminology is slightly going to change here a little bit. All right, so now, here we go. We got an electrophoresis chamber, whatever that means. Electrophoresis, what is it? I don't know what it does. I'm getting ready to tell you. All right, so we've got this chamber, and this chamber has two charges, a negative area and a positive area. So what happens is that, let's say that I have a sample. Blah, blah, blah. There's my sample, all right? And let's say that my sample carries a negative charge. Woo, great. All right, fine. So rules of magnetism, opposite charges attract. Yay! All right, so we get the sample. That sample is a negative charge, and that negative charge is hanging out, and that negative charge sees that positive there at the very bottom, and it goes, ooba, hooba, hooba, hooba. I really like that positive charge. And then all of a sudden, and that little negative ion goes down to the positive charged area of the chamber. It begins to move because they're attracted with each other. All right, we have proper terms in electrophoresis that we need to talk about before we go further. And one of those terms is, what do we call this positive piece and what do we call this negative piece? All right, this positive piece, this is attracting the negatives, right? That's what this is. It is attracting the negatives. So these anions are traveling toward that positive charge. That positive piece is saying, hey, everybody, if you're a negative, come on my way. Come on down. I'll give you a place to stay. Free beer, free food, free everything. Come on. And all of these negative charges begin to migrate. All right, because of that, it attracts anions. And we have a proper term for the electrode that creates that positive environment. And that electrode, because it attracts anions, is called the anode. That is the proper term that we use. So anodes are attracting anions, and anions are negative. So that means a anode has to be positive. Otherwise, this don't work, right? So anodes attract anions, and if they're going to attract them, that anode better be a positive charge. All right, so there's one of how this electrophoresis is going to work. And then up here at the top, we also have formal names for this as well. So this negative area, well, okay, that can attract cations, right? If cations are positive, then those positives are going to see that negative electrode up at the top. And that negative electrode is going to be like, hey, cations, come on down. Free pizza, free beer. Woohoo! Party's on us. And those cations begin to migrate and they begin to move. So up they go. If they were positive, up they go, right? All right, so because they are attracting cations, we are going to call this a cathode. C-A-T-H-O-D-E. Oh my God, what a mess. Where is my crazy mind at today? Can I not spell? C-A-T-H-O-D-E. Cathode. So we have cathodes that are attracting cations. We have anodes that are attracting anions, right? The cathode has to be negative. That way it can attract cations. and the anode has to be positive. That way it can attract the anions. All right? So there's a little bit of confusion there, and the confusion is the terminology of what we call the electrodes. But just kind of keep in mind what those electrodes are actually doing, right? They are attracting cathodes. They are attracting anions, anodes, and those are the proper terms that we use, all right? So, in electrophoresis, in a roundabout way, I had to give kind of this explanation first. In electrophoresis, what we're doing is that we are creating charged environments like this. And these charged environments are going to be made up of an anode, which is going to be positively charged, and we're going to create a cathode that is going to be negatively charged. And this, ladies and gentlemen, is going to help separate various compounds. And these compounds are going to be termed as macro molecules. And I did that macro in big letters. And that's because this is the first time that we are using something this big in a laboratory procedure. Now, when I say big, what does that actually mean? Well, for the most part, when we talk about formula weights or molecular weights of compounds, when we talk about those molecular weights, in a general run-of-the-mill lab procedure, we are working with like 350 grams per mole or lower. Most of the time, that is what we're doing. So if we take a look at various salts that we are measuring out and dissolving in water, if we're looking at various organic flammables like toluene or xylene or dimethylene chloride, those are very often low molecular weights. If we're looking at our health hazards, our oxidizers, our acids, our bases, everything that's mainly in our laboratory area, those have lower molecular weights on them. And those are the things that we use all the time. So we never really dabble into the world of macro molecules. Macro. It's big, right? It's like a Big Mac at McDonald's. These are Big Mac molecules that running around in a lab, and we're going to have to do something with them. All right, so it's my job to separate these Big Mac molecules, these macro molecules. So how do I do that? Well, electrophoresis is going to help me. So what goes on here is that this electrophoresis method is built to separate macromolecules. Okay, so what that means is that I'm going to have really big chunks and maybe some smaller chunks, but still pretty large, and then maybe some really big chunks of stuff. And these chunks are extremely large, extremely big, very difficult to work with under normal circumstances, meaning that normal separation here is not going to help us out too well. Normal separation would be things like your separatory funnels, right? You've all used the separatory funnel probably at this moment, and those separatory funnels do a very good job separating liquids from each other. But those liquids have really low molecular weights, and the stuff in the liquid that's dissolved, it also has very low molecular weights. This is nothing that's the macro world, right? The other separation technique that we've done here is just really some solid liquid extraction. So just basically some funnels. So some Buchner funnels, and you add some solvent, and solvent dissolves one thing but not the other, and we pour it through and we separate. This electrophoresis is simply a separation process. That's all that it's going to do. Nothing reaction-wise, nothing of making a new product, calculate your theory yield and your percent yield. That's not what's happening in electrophoresis. It is simply separation. That is all that we're doing. So that separation has to take place, but the separation is with very large molecular weight compounds. And when I say molecular weights or formula weights here, folks, we are very often talking about 100,000 grams per mole or larger. That's how big these things are. So what types of things would these big blobby molecules be like? I mean, what am I actually working with here? What is electrophoresis appropriate for? Well, number one, it's going to be RNA. ribonucleic acid, RNA. Everything's got RNA in it for the most part, right? I mean, here I'm looking at RNA. It's a genetic coding system. RNA's purpose is something else. We'll talk about that in a completely different lecture. Not in this course, but in a different class. But RNA is a macromolecule. It is very large. It's very big. It has a very big formula weight. There's a lot of carbons, a lot of hydrogens, a lot of nitrogens, a lot of sulfurs. I mean, who knows, right? It just depends on what's actually there and how it's actually made. So there's number one. All right, RNA. Number two is also DNA. Deoxyribonucleic acid. So DNA is another macromolecule. Folks, these things can be 6 foot long, right? If I stretch this strand out of DNA, I can get a 6 foot long piece if that's kind of what goes on. Not a big deal. Very large molecular weights, very macromolecule-y. That's what this is all about. So DNA is going to be appropriate to run in electrophoresis, just as RNA is. I very often call this the brother and sister of the genetic world. And they kind of go along together. They're related in some form or fashion. One does a job and the other one does a different job, but they are very similar. Not identical, but they're very similar. So they grew up in the same family. All right. Number three, another thing that can be ran in electrophoresis like this is proteins. And proteins do a different type of job. They are not a genetic carrier like DNA might be, but proteins really make your body function. So there are certain proteins for certain things, and the way that your body processes food, the way that it breaks that food item down, the way that it releases that and stores it as energy, the whole decomposition and making those products, the way that our eyeballs see, the way that our brain thinks, all of this is really protein-based. And that protein-based chemistry is very important. So these proteins, just like DNA and RNA, are very globby. And those globby molecules are really big and really fat and big wobbly, and we have to separate them sometimes. So traditional separation techniques might not work out the best because I need a little bit of extra help. So all of these, RNA, DNA, and proteins, are very commonly ran on electrophoresis. And what we're doing in this lab experiment, we're not looking at proteins. That's going to be a modified version of electrophoresis. But what we're doing here is that we are taking the idea of RNA and DNA, and we're going to be injecting a sample onto an electrophoresis gel and put it into an electrophoresis chamber in order to separate the components that are on the inside of this sample. All right, so all of these really have a very strong tie to electrophoresis. This is really dabbling into the world of biochemistry. That is what we call it. That's kind of the proper term. Let me write that a little bit better. My pad kind of slipped a little bit, my writing pad. So biochemistry is going to be the area, maybe in a bachelor's degree level or a master's degree level, that focuses on this concept of DNA and RNA and proteins and how all of this interacts and makes bodily functions work and those types of things. That is traditionally biochemistry at its heart. So this is kind of the realm that we're dancing in a little bit here. Very uncommon from what we've been seeing before in the past. This is kind of the first step in that direction of things. Biochemistry does have its own like weird version of chemical technology that's out there, and we would call this biotechnology. And biotechnology, look, my brain and my hand is not working together today. All right, so biotechnology. Biotechnology is typically a 2-year program like Chemtech is, but the biotech spin really puts a focus on the biomolecules. And again, those are carbohydrates and proteins and fats, DNA, RNA, all of that umbrella of things that you might find in a body to make a body work. That is biotech. So with that said, This is your introduction to electrophoresis, and there is way more than that if there are majors on it that we won't be able to get into, but it's my job to kind of give you the basics here. That's what this is all about. All right. Okay, so with that said, let me take a look at maybe a better diagram of an electrophoresis chamber. And the electrophoresis chamber is going to look something like this. So eventually we're going to make it to a point, especially in the lecture discussion here, about electrophoresis and about what this thing does. And what you're seeing is a chamber, and the chamber is the piece where's my pen? All right. Oh, no wonder it's white. Ha 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 ha. I just don't have it together today. All right. So this electrophoresis chamber is going to be an area that's going to be filled with buffer. This is not water. Buffer is really going to be needed here because we're playing off on charges, and that buffer is going to be very important. So the chamber is going to be there. That chamber is going to be filled with buffer. And there's two cables that lead from the top of this chamber. One is black and one is red. The red one is typically the positive one, and the positive one is attracting the anions. And those anions, because they are migrating to that side, if that's attracting anions, this is called the anode. That is what that is. All right. And then up here at the top, we get this black cable, and this black cable is very often negative, and that negative is attracting cations, and because that's attracting cations, this is called a cathode. So the black one is a cathode, and the red one is the anode. All right, they are attracting the cations and attracting the anions and the cations, right? All right, so here is the gel. And this gel is going to be made of a material. We're going to have to make the gels most of the time. They can be pre-ordered, but we're going to make ours. And then this is like a little flimsy jello-like structure. And this is where our samples are going to go. So the samples are going to get loaded up here in the tops of the gels. That could be, again, proteins or DNA or RNA or whatever the case is. And this is a mixture. And that's why we're doing this, because we want separation. And that's what this electrophoresis is all about. So this is a mixture of different sizes, really, really big ones, and then little mid-sized ones, and then little tiny ones. But when I say tiny ones, it's still big, because based on what we're doing and what we're after, that's kind of what we are using the electrophoresis for. So the idea is to take this mixture, and really big ones are going to take a little slower to go through the gel. And then the smaller pieces are going to right through, and they're going to travel at a faster rate through the electrophoresis gel. So this aids in the separation, and it's the separation which is why we're using electrophoresis. And for that reason, electrophoresis does separate, but it separates mainly based on the size of what we would call the fragment. So the larger ones typically hang out at the top, and the smaller ones can travel through quicker. They're lighter on their feet, and they have a little bit higher speed to go through the gel of the electrophoresis gel in order to reach that red cable down there at the very bottom that is positively charged. All right, so with that said, that's where I'm going to stop. And in the next video that we're going to talk about, we are going to discuss some of the samples that we are going to be injecting onto this electrophoresis chamber. So take a break, take a snack, take a drink, and then crack those knuckles, because when we come back, we're going to be talking about samples. We're going to be talking a little bit about theory and some different alternatives if we didn't have electrophoresis at our disposal that we could possibly use for this purpose. So I'll see you in a few minutes. Don't go away. I'll be waiting. Don't leave me hanging.